Okay, so now that we've defined group actions, I want to tell you about really the two most fundamental examples of group actions that appear over and over again. So the first, I already mentioned it in the lecture on the orbit stabilizer theorem. This is that if H is a subgroup of G, implies that G acts on G mod H by left multiplication. And why is this a fundamental example? Well, several reasons. So one reason is by the orbit stabilizer theorem, every transitive action of G on a set X is actually isomorphic to an action of the form in example 1 of G acting on the quotient by a subgroup. To an action of G on G mod H. Specifically, if G is acting transitively on X, then as we saw in the orbit stabilizer theorem, we will take for H to be the stabilizer of any point in X. Another reason why this is a nice example of group actions to consider is the particular case when we take H to be just the identity subgroup. In this case, G mod H is G. We are looking at G acting on itself, G acting on G by left multiplication. And we have the following theorem called Cayley's theorem that says that every group is a subgroup, well, is isomorphic to a subgroup of a symmetric group. More precisely, we can achieve such an isomorphism by this action of G on itself. So, more precisely, the homomorphism corresponding to the action of G on G that we described here by left multiplication is an embedding phi from G into the symmetric group on the set G. So since it's an embedding, I can write the arrow with a hook like this. So every group G is isomorphic to a subgroup of the symmetric group on the set whose elements are the elements of G. Okay. Good. What is the second fundamental example of group actions. This is that there is a second way that G acts on itself. Here we said G acts on itself by left multiplication. G acts on itself in a second way conjugation. By conjugation. What does this mean? This means that I do G dot x is equal to Gx G inverse for all G and x in G. So here both G and x are elements of G, but I'm thinking of G as an element of the group and x as an element of G thought of as the set on which G is acting. Now, it's very important in this example to think about what the terms that we defined in general mean. So we had the orbit and we had the stabilizer of a point. So definition, if G is in G, the centralizer of G, which I will write cent lower G of G, well, this is the stabilizer of G for the conjugation action. But let's unpack what this means. The centralizer of G in G, if we look at the definition of conjugation, this is the set of H in G such that HG H inverse gives back G. So this is exactly the set of elements of G that commute with our element little g. Okay? And as with an arbitrary action, this centralizer is a subgroup of G. So centralizer corresponds to stabilizer in the case of conjugation. Then what's the other thing? We had the orbit. So the orbit of x in G under the conjugation action is called the conjugacy class of x in G. And again, unpacking what this means, the conjugacy class of x, this is the set of all elements y in G that are conjugate to x in G. So I will write this class of x, and this is the set of y in G such that y is conjugate to x in G. So now let's compare what's going on between the two examples. In the example of G acting on the quotient by a subgroup, we know that that action is always transitive. In this action of conjugation, that is almost never transitive. And it's very important and interesting to study the various conjugacy classes, the number of conjugacy classes, how to tell whether two elements of the group are in the same conjugacy class. we will see that there is a very nice way of doing that explicitly for the symmetric group. For now, let's just note that we can write down the orbit stabilizer theorem in the case of conjugation. So orbit stabilizer for the conjugation okay. So we have our set X is G in this case. And we write this as the center of G. So why do we write the center of G? The center of G, this is the union of the conjugacy classes of size 1. Union of conjugacy classes of size 1. So an element X is the only element of its conjugacy class if and only if it is in the center of G. And then this is a disjoint union with the class of X, or class of Xi maybe, I equals 1 to k, let's say, where x1 up to xk are representatives of the conjugacy classes of size strictly bigger than 1. And taking cardinality of both sides, we get what is called the class equation. So we have that the order of G is the order of its center plus the sum of the orders of these classes xi. But by orbit stabilizer, I can write the cardinality of these classes in a different way. I can write it as the order of G divided by the order of the stabilizer of xi, which in the case of conjugation we said is just the centralizer. So the order of G divided by the order of the centralizer in G of xi, and this should be summed up from I equals 1 to k. Okay, and we will see that this class equation is extremely useful for proving non-trivial things about the structure of G. For example, this will be used in proving Silo's theorem. This is also used in proving that a group whose order is a prime power has a non-trivial center. Okay, so let me show you how to prove the second application of the class equation that I just mentioned about the center of a P group. So let's first recall that definition, a P group for a prime P is a group whose order is a power of P. So if we write our group G, what this means is that the order of G is P to the k for some integer k, which is at least 1. Okay? So now the theorem that I was mentioning a minute ago is that if G is a P group, so note in particular that a P group is a finite group. If G is a P group, then the center of G is non-trivial. That is, we can be more precise, the cardinality of the center of G is at least P. The center of G contains at least P elements. Let's see, how do we prove this using the class equation? So we write the class equation for G. So we have the order of G is equal to the order of the center of G plus a sum I equals 1 to k of the order of G divided by the order of the centralizer in G of xi. So here we have the quantity that we want to understand, the order of the center of G. Now, by assumption, the xi, these representatives over here, they're not in the center. That's saying that the size of their conjugacy class is bigger than 1. So they're not in the center, which means that the order of the centralizer in G of xi, this is strictly less than the order of G. In other words, this quotient has order bigger than 1. However, the order of G, since the order of G is p to the k, for some k, the order of the centralizer in G of xi, this has to be p to the ri for some ri less than k by Lagrange's theorem. So remember, Lagrange's theorem says the order of a subgroup divides the order of a group. Here I have a subgroup. So the order of this subgroup needs to divide the order of G. A divisor of p to the k is necessarily another power of p to the ri. Okay, and so what is the order of this term here? So the order of G divided by the order of the centralizer in G of xi, this is p to the k minus ri. And because ri is strictly less than k, this is divisible by p. In other words, this k minus ri, this is strictly bigger than 0. So if I take this sum, k equals, I equals 1 to k of the order of G divided by the order of the centralizer in G of xi, this is divisible by p. P divides this sum. But now we are in good shape. P divides this term of the class equation. P divides the order of G. So P must divide the difference, which is the order of the center of G. Since P divides the order of G, by class equation, P divides the order of the center of G. But there's always one element that we know is in the center. The identity is in the center of G. So the order of the center of G is at least 1 and divisible by p. This implies that the order of the center is at least p, which is what we wanted to show.